Hi everyone, this is Karthika, Faculty of Physics, working in SNS College of Technology. So in this session, I am going to explain about the fiber optic communication system. So this is nothing but the applications of optical fiber. So one of the important applications. So we know that communication is nothing but transferring information from one place to another, so without the loss of the data or minimal loss. So here the fiber will be helpful for the communication system in a best manner. So here we can see the design thinking meets how the optical engineering. So here we have seen the 5 stages. So that is empathize. So understanding data transmission challenges in modern networks. Here we can see the define, that is identifying bandwidth limitations and signal loss problems. So if we see the ideate, exploring optical solution wavelengths as modulation techniques, and then prototype. So building and testing fiber optic system configurations and then test. So we can here measure the performance matrices and optimizing parameters. So here we can see the core components of the optical fiber system. So the important component is nothing but the optical fiber. So in that we have different types of fiber, that is based on the material we can have the glass and plastic fiber, and based on the mode of propagation we have a single and multi-mode fibers. So if we take a refractive index profile, so we have a step index fiber and then graded index fiber. So the optical transmitter is nothing but laser diode or LED we are using here to convert the signal. So we'll send the information as a analog signal that should be converted into the light signal. So light only allowed to the optical fiber. So here we can use the laser diode or LEDs. So it converts electrical signals to the light, and then here the wavelength chosen is 850 nanometer or 1310 nanometers or 1550 nanometers. So in this range we can use the light source. And if we go with optical fiber, we can use high refractive index, that is core we can use, and gladding will be lower refractive index, that is denoted by N2. So the principle of optical fiber is total internal reflection. So in this principle only the optical fiber works. And the optical receiver uses the photodiodes. So in receiver end we can have the photodiodes, that will be a pin or avalanche photodiodes. So that will convert the light back into the electrical signals, and that will completing the communication loop. So here we will have the transmitter, in between we have the optical fiber, finally we have the receiver end. So here we can see the user needs. So the data centers so need ultra high bandwidths with minimal latency for cloud computing and big data applications. And if we see the telecom networks that require long distance transmission with low signal degradation for 5G backhaul and the intercity connections, and then medical imaging. So here the demand precise and noise free signal transmission for endoscopy and surgical instruments. So these are the comes under the user needs nowadays. And here we can see some key technology challenges. So attenuation is nothing but the loss. So how we can calculate the loss is nothing but output power put to the input power. So that ratio will give the attenuation. So here we have the typical 0.2 to 0.5 decibel per kilometer at 1550 nanometer wavelength. So this is the value for the attenuation. And dispersion, here the pulse spreading limits that the bandwidth will be increased. So the distance product and chromatic and model dispersion, so that will affect the signal integrity. So non-linear effect is nothing but 4-wave mixing and then self-phase modulation at high power critical in WDM systems with multiple channels. So here we can see design and solutions and some innovations, that is WDMM technology. So that is nothing but wavelength division multiplexing that will combine multiple optical signal at different wavelength. Next we can see the optical amplifier, that is nothing but erbium doped fiber amplifiers, that is called EDFA. So that will boost the signals without electrical conversion and then enabling ultra long distances. So and we can see the advanced modulation. So in that QAM, QPSK and coherent detection techniques that maximize this spectral efficiency and data rates. So this we can see the lab setup and the testing. So here the essential equipment is nothing but the fiber and then power meters and attenuators, bit error rate testers and then fusion splicer for connections. So here we can see the performance matrices. For a capacity we have the 100 plus gigabytes. Here we can see modern single mode fibers, so that will achieve the data rates exceeding the 100 gigabyte per second. And if we see the loss, means here we can have the 0.2, that is decibel per kilometer, and then lifespan is nothing but 80 plus kilometers. So that is a typical amplifier spacing in long haul networks, so without regeneration. So these are the performance matrices. Here we can see the real world applications and impact. So global internet backbone. So submarine cables carry 99% of intercontinental data traffics, that is across the oceans, and metropolitan networks, here fiber to the home, that they will delivers gigabit internets to the millions of households. And then space communications, free space optical links for satellite to ground high speed data transfer. So these are the real world applications. Here we can check our knowledge through the previous data. So here we have the three questions. So the first one is, which wavelength offers the lowest attenuation in optical fiber? The answer is nothing but 1550 nanometers. So which what does the EDFA stand for? The optical communication, that is nothing but erbium doped fiber amplifier. And the third one is nothing but the principle behind the light propagation in optical fiber is nothing but total internal reflection. Thank you.